let me know if you're reading, you're hearing, and everything is okay. Okay. So if something does not work, just tell me, and I will try to go to the lecture room. Ready to start? Please say yes. At least somebody should say yes. Okay, very good. So today we continue discussing time-independent perturbation theory. Okay, and what I want to do. So it's time-independent perturbation theory. And what I would like to do is to discuss a couple of, let's say, examples. Let's say these are, I mean, they're not simple exercises. So what I would like to do, and actually they are not just exercise, I mean, they may teach us something about the physics of quantum systems. So what I would like to do is just to set up all the steps of the calculation and guide you through the solution. But then all the actual calculations, this is something you have to do it, because in this way you will learn how to proceed. Okay?
Yes.
So the first example we would like to address is the following. Just imagine that you have two hydrogen atoms. Okay? So you have two hydrogen atoms. So you have here with so an atom with electron, and then there is another hydrogen atom somewhere. Okay, and they are far apart. So the distance between the two atoms is much larger than the typical distance within in each atom, in each hydrogen atom. Now, the net Coulomb attraction, if you just count the charges, is 0, because you have two neutral objects, and since you have two neutral objects, then in the dominant, let's say, the dominant contribution, which comes from the fact that just the net Coulomb interaction is 0. However, you know that this is not the case. So the result is that there will be still some interaction between the charges, which does not come from just saying, okay, here you have a neutral object, here I have a neutral object, so these are 0 charge, there is no interaction. So do you know about dipole, multipole expansions in electrodynamics?
Yeah.
Okay. So basically, since positive and negative charges are not on the same in the same place, that there will be some net interaction, which in general will be much weaker than the direct Coulomb interaction. So indeed, it does not scale like 1 over r, but it will scale very differently. So this goes in this particular, I mean, this goes if you take two neutral molecules, and the weak interaction which occurs between these atoms or neutral atoms is what is called van der Waals force. So van der Waals. And now the potential between, so if this is the typical distance r, the potential which govern this will go like some constant c divided by r to the 6. Okay, so it decays much faster than Coulomb. Coulomb is 1 over r. This will decay 1 over r to the power 6, and it turns out that this, so I mean, this constant is negative. It's a weak attraction between the two atoms. So the exercise of today is try to use perturbation theory to determine this okay. So we will see two things. So by just carefully doing the multiple expansion for this particular case, we will study hydrogen atoms. So this is something much simpler to do, because you know the wave function for each hydrogen atom. And so we will see what is the origin of the R to the 6, and then and this comes from for the multiple expansion. And also we would like to understand how to get the constant. So the constant which will give you the strength of the interaction between these two hydrogen atoms is something we can determine in perturbation theory. Okay, so this exercise, or this example, has several important byproducts for you and for this course. So first of all, we just learn some piece of new physics, if you wish. But second, I mean, I think it will be very useful, because in a moderate complex problem will tell you how to approach it by using perturbation theory. Or at least, let me say, the first thing that we have to see when we start a problem like this is to understand under which conditions we can use perturbation theory. So let's start with the problem. So what is the Hamiltonian of the whole system? So the Hamiltonian of the system is given by, let's say, the Hamiltonian of the first hydrogen atom plus the Hamiltonian of the second hydrogen atoms plus the Coulomb interaction between the two atoms. Okay, so let's see, just to, I mean, I will write it the three terms separately to see what is there for. So let's see first H1. So H1 is simple. This is something you studied. So you have p squared over 2m plus p1 squared plus p1 squared over 2m, so the electrons and the proton, and then you have the interaction between them, where so you have e squared over r1. Okay, and the same is true for H2, for the second atom. So you have p2 square over 2m plus p small p, so the electron, 2m minus e square over r2. Okay, so r1 and r2 are the distance. So let me say, if I can do it better here. So if I have if you have the two atoms, so you have this, and this is the electron, so this is r1. Okay, and similarly you have r2. Okay, now just keep in mind that in this problem you have so I should specify what is this r. I'll do it in a second. Okay, the only thing I want to tell you is that just keep in mind that R1 and R2 are the distances between the electrons and the protons in each of the two atoms. Okay. Now, how to define? So the first thing, which is very important, and we should be very careful about this. You should be very careful about this. Is to define the let's say the Coulomb repulsion, because the Coulomb repulsion will need to specify all the position of the 4 charges. Okay, so, and let me specify here. Okay, so I just call R1 the position of the first atom, sorry, of the nucleus. R2, given, I mean, you have some reference frame, which is not important to specify now, but depending on this reference frame, R1 and R2 are the coordinates of the 2 nuclei. This means that the position of the 2 electrons will be R1 plus small r1 and R2 plus, okay? So is this clear? Hello?
Yes. Yes.
Okay, very good. So this means that now I have to write down the 4th term in the Coulomb interaction. The 4 terms of the Coulomb interaction is the 2 positive charge, 2 negative, and then positive, negative, and negative, positive. So let's see, let's do this with care. So I have E squared over R1 minus R2. Okay, this is what? Just please.
Coulomb interaction between 2 nuclei.
Very good. Then I have another term which is plus E squared of R1 plus small r1 minus R2 minus R2, okay, which is the Coulomb interaction between the 2 electrons, okay? And then I have the next 2 terms, which are minus sign, and it's E squared R1 minus R2 minus R2 small minus E squared, and then I have R1 plus R1 small minus R2 squared. Okay. Now it is important, you should be very careful here, that to just consider the vector. So you have to take the distance between the points. Okay. So typically many students just put Coulomb interaction is just the modulus of R. Okay. So here, if you do it directly, just putting small r, large R, whatever, this is wrong. So you have to take a given reference frame, just individual, I mean, point out where are, I mean, the atoms and the 4 charges in your reference frame. And here we just call it capital R1, capital R2, and smaller one, sorry, capital R1 plus smaller r1, because we want to use the relative distance between electrons with respect to each nucleus. And this is the way in which we write. Now, if you look at this problem, okay? So can you tell me, according to you, what is the, let's say, let's put it in this way so you see everything. So can you tell me what do you think should be a small parameter that we need to use to build up our perturbation theory? So can you just spot something which is a small quantity, which is very important to keep in mind for the whole problem? Because this is the key, okay? So when you have to solve a problem and you think that perturbation theory may work, the first thing before doing calculations, you have to look at the problem and find if it exists. I mean, it may not exist, but at least try to find if there are regimes in which there is something which is, I mean, which looks like a small parameter such that you can write your Hamiltonian in such a form where this is something where you can expand upon. So this is the initial problem for charges with kinetic and Coulomb interaction. Can you see something which looks like a small parameter in this problem?
It's I think it's Coulomb interaction.
With respect to what?
And which include the nuclei, because the distance between two nuclei are very far. So
very good. So what is the small parameter? So in order to define the small parameter, I need something dimensionless. So what is, I mean, what is something that we can use as a small parameter?
It's
so
like
you are close. I mean, say Coulomb. If we say is just Coulomb, this is not true, because
yes.
Coulomb includes also terms that lead. I mean, yeah, that lead to the formation of the atom itself. So it cannot be small.
I mean, V Coulomb.
Not really. So tell me something else. Look at this picture. Okay, so let's say this is something like R. Okay. So what is so basically what is so in multiple expansion there is a small parameter. Do you remember? So let me say the following. I try with okay. So let me say the following. If you have so this is classical, okay? So if you have two spheres, two classical sphere which are charged Q1 and Q2, okay? Now, what is the interaction between these two?
It's Coulomb.
It's Coulomb, very good. So if you put in the center of the sphere, I mean, just imagine, I mean, the picture is not good. Something which is minus Q1, and here you put minus Q2. What is the interaction?
Yeah, Coulomb attraction. No,
what is the total charge here? Is 0. The total charge here is 0. Then the interaction between these two is So if you have neutral objects,
Van der Waals interaction.
no, yeah, but let me
No.
ask the following.
No Coulomb interaction.
So if the center of mass of the positive charges is in the same place as the center of mass of the negative charges, okay, I can draw you this, which is just imagine this. So just imagine that you have a sphere with a hole, okay? And the sphere with this hole has positive charge K1, and you put inside the sphere a negative charge minus square in the center. And the same is true here, okay? So this is Q2, and inside is minus Q2. What is the total charge here? Total charge.
0.
Yeah?
0.
Very good. So in both cases, it's 0. Okay. So the Coulomb interaction is 0. Okay.
Yes, yes.
Yes.
Very good. So now I just tell you something. I want to do something else. I want to do the same thing. So I have this sphere with a hole, but then I put minus Q1 here and minus Q2 here. Okay. Now tell me, what is the total charge of this object? This symbol, what is the total charge?
0.
0. What is the total charge of this object?
It's 0 too.
Very good. Now, can you tell me, is there any, oh, okay. Is there any interaction between this object and this object? Or no?
Yes, there is.
Very good. What is the reason why there is an interaction?
Because the charge is not isolated.
No. So what is the difference? So I just draw it in this way. What is the difference if you put a negative charge here or you put it here? So I just use colors, okay? So
Professor.
Yeah.
The charge inside the circle, is the circle some kind of conductor or something, or it's just
it does not for the discussion here, it does not matter. Just take an insulator, okay? So
okay.
there is no induction charge, nothing.
So, Professor, when we talk about total charge 0, is it known? We are now going to dipole moments.
This is my question. So can you explain why there is a dipole moment if you put a charge outside here or there?
I don't know if this is the right thing, but I think.
Can you speak louder? I do not hear you.
Can you hear me?
Now, yes. Please go ahead.
Okay, this is. I think. Wow, this is stopping again. Hello. Hello.
Yes.
Yes.
Oh, okay. So I am saying that there is some sort of screening. I think if we.
Okay. No, I understand. So this is not a good example because I mean there is no screening. These are insulating charges. So insulator. So I forget about the screening. I want to do another example.
Is this related to the symmetry of the problem? Because
very good. It's related to the symmetry of the problem. Now, what is the difference if you put a charge here or outside there?
Yeah, because you have the dipole moments, right? If you put the charge outside, and if you put the charge inside, you will.
Very
you'll
good.
be
So that's what I would like to have. I mean, the difference between these two cases is, for instance, that the center of mass is not in the right place, in the same place, okay, of the positive and negative. So there will be a dipole moment. Now, in this case, you may have additional effect like quadrupole or higher moments, okay? So I don't want to discuss for the moment. What I want to say is that if you have, so let's say the following. I don't know how to draw it in a nice way. Let's see. So let's see if, so if you have two charges, okay, positive and negative, which are very, very close, okay? This is distance D, and this is distance R. If D goes to 0, okay, let's do this example. If D goes to 0, what is the interaction between, what is the Coulomb interaction? The Coulomb interaction would be 0 because basically you have 0 charge, okay? Now, if you have, there is a small displacement, so, or you have an extended object, okay? Even if the total charge of this is 0, and this is 0, since they are positioned in different places, this may lead to some residual interaction. Is it clear?
Yes.
Very good. So if you see this problem, in this problem, what is the small parameter which appears? The small parameter is the distance between the two charges over the distance between the two blobs, okay? This parameter is much smaller than 1. So the dimension in the example I gave you before, the dimensions of, let's say, typical dimension of the atom is much smaller than the distance between the two atoms. Okay?
Yes.
Now, we would like to use this small parameter as a way to do perturbation theory. Is this clear or not?
yes, so you're going to use this assumption to do multiple expansion and then you go to perturbation theory. Is that
Very good.
correct?
So what is the so can I so besides the specific problem that we are considering now, what is the strategy? The strategy is the following. You just look at your problem and try to see if there is a regime, or if the regime that you would like to consider contains some small parameter, and then you try to see if you can use this in perturbation theory. So by looking at this problem, then you see that in the same way I said before, the distance R1 and R2 over the distance capital R is something which is much, much smaller than 1. Okay? So then I can do multiple expansion. And let's see if I can use this multiple expansion to do perturbation theory. Is this clear?
Yes.
Okay.
Yes.
So next thing is to do, So you see, up to now, I'm not doing any, so there is no quantum mechanics. This is just classical charges, okay? So the thing I would like to understand, and this is something you did when you study multiple expansion, you had to study this type of problems. So you have R plus D, okay? And you want to see an expansion in D over R much smaller than 1, okay? This is the thing that you have to apply. So you just write this as the square root of R squared plus D squared plus 2D dot R, okay? And this is, you take out 1 over R outside, and you have 1 over R. Yes, just a moment. I finished to write, and then it's 1 plus 2D over R plus D squared over R squared. Yes.
So why is it not R minus D?
It does not matter. It can be minus whatever. I'm just saying this is the structure. You see that what we want to consider is just an expansion. So you see that this is already R1 minus R2, that is the distance, okay? And then here is R1 minus R2. So you just take this one, okay? This you can write as R1 minus R2 plus R1 minus R2, okay? So this is something small as compared to this, okay?
Oh, okay.
So you see that, you see here is just R1 minus R2 plus R1, okay? Here is R1 minus R2, sorry, minus R2. So you see that the important thing is that you have all these 1 over distances in which you have R1 minus R2 plus something, a distance which is small as compared to R1 minus R2. Okay, so
okay,
in all these 3 cases, the expansion is the denominator that we have to consider is of this form. Okay, so D can be R1, can be R2, can be R1 minus R2. Okay, so and then we are going to expand. Since D over R is much smaller than 1, we just expand this. So I wait. R1 minus 1/2. Okay. Then I have D squared plus 2D over R squared plus, and this I don't remember, so I have to read it, 3 over 8, and then I have R to the 4th, R dot D twice R dot D to the power square plus, okay? So let's see the expansion. This is order 1. So this term here is order D over R, okay? This is D square over R square, and it also this D square over R square, okay?
yes.
Then you have other terms which are D over our r to the power cube and things like that. Now, what you have to do, and this is something you have to do, you just apply this expansion to all these three terms. Okay, this term is already done, because what we want to call at the end is this, we call it r. Okay, is the distance between the two nuclei. And then you have to do the expansion I gave you before on this, and on this. Fine. So let's see. Do you see now? Yes. Okay. On this and on this. Wow. Okay. So now this you have to do it yourself. You have to do it yourself. And then if you do it correctly, and we are going to check it if it does not come out right, you will see that all the Coulomb interaction will have this form. E squared over r cubed, and then you have x1, x2 minus, plus y1, y2 minus z1, z2. What are these things? So z1, sorry, let me say, write it this way. R1 is equal to x1, x2, sorry, x1, z, sorry, x1, y1, z1. And R2 is equal to x2, y2. These are the two coordinates. Okay. Now, it is important that this result, you get it if you assume that R is along the z direction. So, I mean, does not really matter. You're just assuming that, you know, you just take the z direction in the direction of the line connecting the two atoms. Okay.
Okay.
Now, this dipole-dipole interaction has as a small parameter, this is important because you see here, there is no small parameter related to some coupling constant. The small parameter is related to the fact that the distance between the atoms, so the relative distance electron nucleus is much, much smaller than the distance between the two atoms. Now, why this is, do you think this is reasonable? Yes. But there is some extra underlined assumption that we are making here, which is not completely written in what we do. So you studied the wave functions of the hydrogen atom. Okay, let's consider for the moment the ground state. The ground state is a wave function which is localized, okay, with within some distance of the order of Bohr radius or whatever, which is localized around the nucleus. So you know that the x1 or x2 such that will give a contribution to the integral will be always confined to these small distances. Okay, so you're making also, and I mean this parameter is small because you're putting also some physical knowledge into the problem. You know that the position of that are relevant to describe the properties of each electrons cannot exceed the typical radius of the for instance, the ground state orbital. Is this clear or not?
Sorry. Can you repeat the last point?
Yes. So let's say, do we agree on this on this expression? Suppose that you just got it, okay? Okay. Now, my question is that, is the dipole approximation valid in this case? This is legitimate, okay? If you have static charges, you just say, I take 4 charges, this example, okay? So let me draw it this way. So suppose that you have this situation, okay? So is the multiple expansion valid if I consider this case? Yes, because this distance is much larger than this distance, okay? Very good. So then I ask you, I ask you to consider a different situation. If you have 4 charges of this kind, do you expect dipole approximation to be a good approximation?
No.
No, very good, because this distance is more or less the same as this distance. Okay, so dipole does not work. Good. So I go back to our problem. Our problem is of we want to study the effective interaction between 2 hydrogen atoms. Okay. So here there are no, I mean, we don't have static charges. It's not the electron is in a given position. Okay. But you know something else. You know that each electron is localized around the nucleus. Okay. The wave function rapidly decays to 0 when you move slightly away from the typical radius of the orbit. Okay. So you don't know, obviously, what is the position x1 or x2, because these are given, I mean, you know the wave function. It's not that you have static charges, but you know that each electron is localized. So this x1 and x2 for sure will be much smaller than r in all those places where the wave function is different from 0. Okay. It's okay. Is it clear now?
Yes.
I want to hear no, if there is some no.
Actually, no.
Okay. So what is not clear? So let's put it this way. Okay. So this is plus, okay? And this is the electron minus, okay? So can you tell me briefly what is the electron? The electron is something like, so suppose that we are in an orbital 1 over s. So basically in 1 over s, the wave function will do like this, okay? The probability to find the electron in one as a function of the distance, so this is R1, for example, okay, will rapidly decay to 0. Okay? Yes or no?
Yes.
Okay. So basically, you don't know. I mean, it's not that you can say X, so R1 is this or this is the radial part. But you know that all possible all possible positions where you will find the electrons are essentially confined in a small region. Okay? So this means that X1 and X2 are operators. So when you are going to solve the Schrodinger equation, I mean, these are observables. But the position, since you know that you have to deal with hydrogen atom, means that the average position will not be 60 kilometers, okay? But it will be just given by the probability to find it within the 1/s orbital, okay?
Okay.
So now I have the next thing I have to do is I have to consider this as a perturbation to the H0. So what I'm going to do is I will consider just the ground state. So I will consider the orbitals psi 1, 0, 0 over 1 and psi 2, 1, 0, 0 over 2. Okay. Do you know about fermions and bosons and symmetry and asymmetry? And
Yes, yes.
okay. So this is symmetric. So you know that since the two electrons are fermions, okay, this is symmetric. So in order to anti-symmetrize, we have to include also the spin part. Okay. But the spin part does not play any role here. Okay. So this is phi 0. Okay, phi 0 is just the two ground state orbital of the first electron and second electron plus some spin part. But the spin part we can forget for the moment. So it does not really important. Okay. Now, what is the first order correction to the state, to the energy? Do you remember in perturbation theory?
It's phi 0.
So it was
Yeah, it's
phi
like
0,
phi 0, and then the potential and phi 0.
Phi 0. So
The
it's the
actual-
average value of the potential. Okay. Let's see here. So we have to take average value of this object over this wave function. Okay, we do it in real space. So in real space, this, for instance, if I would have just one coordinate, would be something like dr phi star of r v of r phi of r. Okay, if I have two, I mean, this I just write for one r. If you have two, you have to write it properly. So can you tell me what is the first order correction in this case?
Phi 0, I think.
Very good. Why?
Because the wave function is symmetric and the potential is
Antisymmetric.
yeah,
Okay,
antisymmetric.
very good. So in first, you see the integrals over x1 and of the one variable and two variables get separated. And as you pointed out correctly, this is antisymmetric, so this would be 0. Okay. So for this particular problem, first order correction is 0. But now, if first order correction is 0, then immediately see that the interaction between the atoms of the, between the atoms will go like 1 over r to the power 6. Because second order correction, I mean, in principle, it may be that also the second order correction is 0, but if, so to the second order, basically I have to, let's do it, okay? So second order correction, then do you remember the formulas? The second order correction was something like E2 is equal to sum over m different from n E0 of n minus E0 of m. Sorry, we do it for the ground state. So we just put here 0, okay? And then we have phi 0 of, let me write it correctly, 0, 0. And then I have the interaction, which is x1, x2 plus y1, y2 minus z1, z2. I have phi 0 of m modulus squared. And then I have to multiply E force over r to the 6, okay?
Yes.
Now, what is what is E0? E0, so let me specify here. E0 is just twice the ground state of the hydrogen atom. Right? So basically, you just evaluate the energy of the ground state energy of the hydrogen atom. I just call it Eg. This is twice Eg. What does it mean M here? M it was genetic excited state, but now we have two particles, and so we have N1 L1 M1, and then we have N2 L2 M2. So we have the quantum numbers for the first electron, which are principal, angular, and projection, and the angular momentum, and the quantum lambda for the second. And E0 correspondingly, E0 of M will be given by what? E N1 plus E N2. Because we know that the energy depends only on the principal quantum numbers. Okay.
Okay.
Now, okay, so I mean, now there is something you have to do. You have to do these integrals here. Okay. So the integrals that you have to do are separate. I mean, you have to do the integral for phi 0 of n1 L1 M1, and then you have either x1, for instance, or y1, and then you have phi 0 of 1, 0, 0. So you have to compute the matrix element for between the ground state, the 1s orbital, and generic excited state on the first atom. And this you have to do it for x, for y, or for z. Okay. Since you know the hydrogen atom wave function, this is something you can do. And what you find, what you have to find, so I'll tell you, is that there is a selection rule which tells you that L1 should be equal to 1 and L2 should be equal to 2. So out of this incredible sum with all possible L and M, L1, L2, and so on and so forth, only those terms will contribute. Okay. Now, sorry, there is something else I want to tell you. Yeah. Still, this is not enough because you have to find that M1 should be equal to 0 and M2 will be equal to 0. This means that all the matrix element in which L1 or L2 are different. So this is not 2, is 1. Sorry, I just wrote it. So only the matrix element in which L1 is 1 and M2 is 0 will be different from 0. All the others are 0. So so out of this, all this sum, only this is equal to 1 and this is equal to 0, this is equal to 1 and this is equal to 0 will contribute. Still, I mean, the problem is pretty complicated. Well, don't worry. There is an extra approximation that I tell you that you can do, and this will simplify your life. That is the following. So do you remind me how the excited state energy depends on the quantum number, on the principal quantum number?
1 over n squared.
Very good. So this goes like 1 over n squared. So you see the difference will rapidly, I mean, this term will rapidly go to 0. So you're allowed, I mean, you can do in principle the exact calculation, but don't do it. Just assume that since this term will go rapidly to 0, then you drop it. And this is nice because if you drop it, I just rewrite it here so that you can see. If you drop it, then you say, okay, this is nothing else than one 1/2 EG. And this is equal, I think there was a minus sign here that I have to put. And this is equal to minus E squared over R6. Then I have 2 EG. And then I have sum over, yes, just a moment, over N1 and 2 of phi 0 of N1 1 0 and 2 1 0. Then I have x1 x2 and then I have the ground state. Okay, yes, tell me.
How do you get the minus sign?
No, I simply forgot because it was like this. Oh, sorry, no, there is no minus sign. I simply, so it was, sorry, if I just write this way and there is no minus sign, you're right. What I wanted to say is that EG is negative, okay? The value of EG is negative. That's what I wanted to say, okay? So to summarize, so let me write this way because I like it more. So up to here, we saw that since EG is negative, I just put the absolute value. So we see that the van der Waals interaction is attractive. It scales like 1/2R6. And it has this form. The last thing one has to do is to compute this integral, okay, to find the actual result. This is something you have to do it yourself. I'll just give you the result, okay? So the result that you have to find is that VR goes like minus 6 square Bohr magneton to the power 5th divided by R to the 6th. So you see? Now, let me say that we already got the minus sign. Minus sign, we got it. We got it R to the 6th. Now that it scales like Bohr radius 5 divided by R to the 6th, this you can get it by dimensional analysis, okay? I mean, this form is clear that this energy, so E square over some distance, okay? So since we found that this goes like R to the 6th, the rest should be like going like 1/E squared times distance. And you can express for an hydrogen atom, the natural distance is the Bohr radius, okay? But try to do this and see if you get even the coefficient. So summarizing, and then I really would like to do something else in the last, let's say, 20 minutes. Summarizing, when you have a new problem, just first you have to analyze it to understand if there is any regime, or if it does exist. It may not exist, but if there is some regime in which perturbation theory can be applied, then first of all, you have to understand what is perturbative. This is crucial. I mean, you cannot just do it blindly. Okay? Once you see, you just apply the rules that we saw together. And afterwards, you have to check when those results that you find are consistent with the fact that you apply perturbation theory. Okay? So perturbation regime and is not something you can do it without thinking. Okay? This is something important. So just use this example to work out all the details. And I really would like to stress, the important details are not just the calculation. Important details are also related to understanding when the approximations that you're doing can be applied. Okay? So next week, next Monday, we will do some, and next Tuesday, we will, I will give you two other exercise or problems of this kind where you have to work out really in some details perturbation theory. Something which I would like to start now is something different, that is the last chapter of perturbation theory, that is time dependent. Okay, so in the remaining time, what I'm going to do is I'm just going to discuss or to introduce, let's say, time-dependent perturbation theory. So I would like to spend these minutes just by introducing the main problem. You will see that there are issues which are completely different from the previous cases. So far, I remind you, we just did time independent. So the problem was I have a Schrodinger equation that I don't know how to solve. I have a Schrodinger equation, I mean, eigenvalue equation that I know how to solve. And I just use this knowledge to build up approximate eigenvalues and eigenstate of the, say, difficult problem. Now, in time-dependent perturbation theory, the problem is totally different. So I have the time-dependent Schrodinger equation, okay, and I have some Hamiltonian that I write this way. Okay, so the difference here, the important difference, is that now the perturbation is time dependent. Now, this is very important because since the perturbation is time dependent, then I mean, we cannot talk. I mean, we have to describe the full problem. I mean, the Schrodinger equation, the time evolution of the Schrodinger equation in general. Okay. So there are no eigenvalue, eigenstates of the full problem. So here the question is that, can I construct a solution of psi using knowledge of H0? Okay, so a good approach might be to start with what we know for H0. Now, I have a question. If lambda is equal to 0, now, if lambda is equal to 0, then, and phi 0 of n with energy E0 of n. So can we write a generic time evolution of the state? Yes, it is psi equal sum over m. Okay, sorry. No, I want to use it. So suppose that you know psi at times t equals 0. Okay, suppose that you know, and you just write it as a sum over m cm phi 0 of n. Okay, so this you can do it because phi 0 of n is a basis of the problem. So can you tell me what is psi of t? So this is a question for you.
Hello, can you hear
Yes,
me?
yes.
Yeah, so psi of t would just also be the summation from m c of m, but now it depends on time.
Yeah.
Yeah,
How?
and then we have exponential minus I.
Very good. E0
Yeah.
of mt,
Of,
right?
Yeah, over the Planck's
Yeah, so I just put h bar to 1. Okay.
okay. Yeah.
So this is the solution. Very good. So now the question that I want to see is to do the same for lambda different from 0. Okay. So a good starting point for lambda different from 0 and to say, okay, I just try to do something similar where psi of t is expressed using the same approach, but now I just say, okay, this is sum over m. Sorry.
Sorry, Professor.
Yeah.
What if we write the wave function at t equals to 0, we include some perturbation term?
No. What I wrote here, this is valid only for lambda equals 0. Okay.
All right. Yes.
Is this a question or is it a different question?
Yes.
No. This is valid only for lambda equals 0 here.
I see.
Okay. Now, what I want to, but I really need this expression, this one, in order to try to construct a perturbation theory for psi of t when lambda is different from 0. So the starting point is that I just say, look, I take the same expression as before, minus E0 mt phi 0 of m, but the main difference that I do is that I just say, look, I just take, so I just use this basis. The only difference is that now this coefficient will become time dependent. Okay? So the idea is that you see that when lambda is equal to 0, these coefficients are given and do not change in time. But then when lambda is different from 0, I just take the same expression, but I assume that these are time dependent. If you assume that these are time dependent, this is just the most general expansion that you can do for a wave function, okay? Because the problem goes into the determination of C through some differential equation. Okay?
Sorry, Professor?
Yes, yes.
In the case when lambda is different from 0, I think the time evolution becomes exponential minus IEN, not EN0. Yeah?
Now,
Because the Hamiltonian is not
no,
just
yes, I know, I understand.
H0.
So what you say is the following. If I have psi of t, the evolution is just e to the minus I h times t psi at times 0, right? This is what you say.
Yes.
This is true, no question. However, I'm not saying what is the evolution. I'm just saying that if I have so let me say the following. If I tell you, look, if I want to write, just forget for the moment what I wrote before. So I have a problem, I have psi of t, okay? I just want to represent it in a given basis, okay? Can we, so do you agree that, okay, I can always write something like Bm of t phi 0 of m. Do you agree?
Yes.
So this is because I'm just taking a basis and I'm just saying the generic psi of t is given by some coefficients Bm of t that I have to determine. We don't know this coefficient, but I can always write like this, okay? Now, for what it comes later, what I'm just telling you is that, so I prefer, it's convenient to just take this Bn as C m of t times e to the minus E0 of mt, okay? This is just a choice, but it's not that I determine the evolution in terms of H0, okay?
You mean there is no relation with the time evolution?
Okay, can you speak louder? I do not hear.
Sorry. You mean there is no relation with the time evolution? No?
There is no relation because I still I have to determine what are the Cm, okay?
Yes.
So far, I did not specify anything. The only thing I'm doing is that I'm just rewriting, I'm just choosing the basis in such a way that it will be convenient for the discussion, as you will see in a second. You can check, you can work with this expansion with B, or you just take this C is a totally equivalent. Just the expressions will become easier. Okay.
Okay.
But you can just take this expression here with the b. The discussion will go exactly in the same fashion. Now,
Sorry, Professor. Why don't you put the first order correction like psi M1?
I have to do it in a second, okay?
Yeah.
Just a second. I will go there. So I just rewrite psi of t is Cm of t e to the minus I e0 of m of t times phi 0 of m, okay? So, and I remind you that the Schrodinger equation is I d dt psi of t is equal to h0 plus lambda v psi of t. So what I do, I just take this and I plug it in the Schrodinger equation. So I have to take the derivative of time of psi of t is equal to sum over m of c dot m of t e to the minus I e0 m of t phi 0 of m plus sum over m of cm, and then I have minus e0 of m e to the minus I e0 of m of t. Okay? Is it okay?
I think the last term CM, I think it is still a function of t.
Where?
The last term in the derivative.
Yeah? What I did it wrong?
I mean, CM is it not?
Ah,
still
yes,
a
yes, it's function of t. Yes.
Mm.
Okay. Okay. On the other side, I will have. So I just write it in two pieces. Okay.
Professor, where is the I on the left hand side? I mean,
No, I'm just showing what to do with the derivative. Then I have to put the I. If you want, I can put it here. Okay.
oh, okay.
I'm just showing you first how to take the derivative of this, and then I have to apply the second thing, and then I put everything together. Okay. Then I have h0 plus lambda v to psi of t. This is equal to what? When I apply h0, okay, to psi of t is just sum over m of cm of t e0 m e to the minus I e0 m of t phi 0 of m plus lambda sum over m cm of t e0 m to the minus I0 m of t v applied to phi 0 of m. Okay? Right? So then I have to put everything together and I will write you the result. So you will see that this term cancelled with this. Then I just multiply. So what I do is the following. I just project the Schrodinger equation on phi 0 of n, okay? To get an equation, a set of equations for the coefficient. Yes.
Professor. Oh, sorry. My bad. I I thought it was something else. Sorry.
Can I go on?
Never mind.
Okay. So if you just multiply from the left with phi 0 of n, then you will get an equation for the coefficient dCn dt is equal to lambda sum over m of phi 0 of m n v of t phi 0 of m, and then you have e to the I e 0 of n minus e 0 of m times t. Okay, so this is nothing else than the Schrodinger equation, the same as the Schrodinger equation, but projected on this, using this as a basis. Okay, so up to now I did nothing rather than rewriting the Schrodinger equation in terms of the coefficient Cn, because I just use psi of t as a function of this coefficient. Next week, we will just see how to construct the perturbation theory on this. In part, this is what what you said before, because you see, if lambda is 0, then the coefficients are given, do not evolve in time. And then I want to do a perturbation expansion of this equation. Okay? So I think it's time to go for lunch. We'll continue next Monday. Okay?
Okay.
Yes.
Okay.
Thank you.
Bye-bye.
Thank
Ciao.
you. Goodbye, Professor.